So notice that agent 2, you're saying agent 2 pays 0.5, and agent 1 pays 0. Okay? Can they manipulate that? So it's interesting because agent 2 has more flexibility and yet pays more than agent 1. So perhaps agent 1 do something, or agent 2 do something about it? Yeah?
Supposing there was a third player turn 1, agent 2 would say that I'm willing to pay like, I don't know, 100. So with the two-player game, you can't actually manipulate it right now. If player 1 was, if all of them were playing on the first turn, couldn't
Why would he play 100?
Because he would pay the price of the second.
Yeah, but what if that's, say, 99?
It's still not information.
But that's not good for him. He pays 99, he only has a value of 0.7. Pays 99, and he makes a utility minus 98.3. That's not good.
Well, what if the agent 1 pays like the previous highest value if there's no one else?
No, but I think, yeah, you could do that. But I'm just looking at, the mechanism that you suggested for the pricing. So they pay each kind of the second price in a sense, right? There's no manipulation there. Okay? So in this case, but that's not generally the case, right? So because we saw at the beginning that the second price, as such, is not always the best. What can happen, right? So the first example, sometimes you can manipulate with the second price. I guess I should have put in an example here. So what's okay, so P2 is 1.
So suppose the example was P2 the value of 1, P2 H2 the value of 1, and he could manipulate the second price by postponing his arrival.
Yes, that's right. Could he?
Yeah, because then he would be chosen in the second time slot, or paying 5.
The pay 1.9. Yes. But anyway, so in a way it's the simple example is.
No, that's good.
Yeah.
That's payment. Oh, nice.
So if V1, actually V1 would be 0.2. That's an example. Okay. So if V1 would be 0.2, yeah. The second price is no longer 7%. Right? Or is it? What could he do? What could an agent do? So V1 is 0.2. Anyone else from the audience?
Are we under the first come, first serve or the greedy?
Greedy.
Greedy.
Okay.
Well then,
So we apply.
it doesn't change anything.
No.
Just instead of paying 9.2 cents.
Who pays what?
I mean, if you change the value of agent 1, it's now 0.2.
Yeah.
According to the greedy schedule.
No. So I mean, let's look at new setting where V1 is 0.2, right? The real value of V1 is 0.2. Is there any agent who can manipulate that if we apply the second price? Okay. So it's still the case. So if we apply the second price option and V1 is 0.2, V2 pays 0.5, right? And V1 pays 0, right? Okay. What if V2 declares 0.4 instead of 0.5?
Okay.
Yeah?
Then again, later in time 2, a base point.
He pays 0.2. Okay? I don't know if I can write it down somewhere. So, okay, so that's it's a bit tricky to write down, but I can. I'll just repeat it.
There is chalk now.
There is chalk, but I don't know if you can actually see it.
We can.
Yeah? Not with my handwriting, no? Okay. So, if we have the allocation where you have V2 is equal to 0.7 here, and so and then we have here V1 is equal to 0.2, and we have here V3 is equal to 0.5. Okay. Can you see this? Yes. Okay. So, okay, so in that case, if we would do the greedy allocation with second price payment in each option, right? So V2 would be allocated. V2 would be allocated. That's an item, and the transfers of V2 are minus 0.5. Right? Payment is 0.5. And then V1 would be allocated, and transfers of V1 is 0. Okay. Now what V2 at this point can do is it can get actually the item for cheaper. Okay.
Yeah.
Because it's the second price here is cheaper because this agent is here, but his price is lower than that agent's price. Okay? Because this agent is lower than that agent, it's actually better to win here than to win there. Okay? So therefore, the agent wants to actually delay, so it could do that in multiple ways. So it could declare different different arrival, for example. So it could misreport and say, I'm not available in the first time slot, only available here. Right? And then my price would be. Okay. What time are we?
Still an hour.
Okay.
Equals.
So this is strange, isn't it? Because I said before that greedy was monotonic, I said. And I said any monotonic algorithm, we can design payments that make it incentive compatible. So does that contradict what I just said? Or not? I hope not. Otherwise I'd be telling you nonsense. The problem is with the payment rule, it's still not good enough. Okay. What should the payment really be in this situation here? So this situation, let's go back to the proper situation once. So here, we've got V2 here. Okay. Okay. What should the payment be of V2? Yeah.
We want V2 to pay 0.5.
No. If V2 pays 0.5, he can manipulate and get it for 0.2.
Yes, but if we make him so that even if he takes in the second time slot, he still would have to pay 0.5.
But how can we force that?
By making him pay the second highest bid for each time slot he's been in.
But then he can manipulate again. He can say, I'm not here, this time I'm not available. I'm just available. Yeah?
Assuming that both functions are for the same item, he could pay the sum of the evaluation of the other players that won't.
It's even worse, I think. We want to reduce the payment, not increase.
0.4 or 0.3 maybe.
Yeah, maybe. But even if it's how do we determine 0.3? Where does that come from? Why? 0.3,
It's
right?
greater than 0.2 and less than 0.5.
Yeah, maybe. But what if, what if the agent would report 0.25, right? So what if his true value was 0.25? Okay. His true value was 0.25. Now we're charging him 0.3. Okay? Because he gets allocated in the second slot now. Instead of getting allocated in the first slot, he gets allocated in the second slot. Right? His true value is 0.25, and now we're charging him 0.3. So it's not individually rational. So the thing is that he could do better. This is the basic idea of the payments. He could do better by misreporting, and then he pays 0.2. Okay? Let's charge him 0.2. Let's look at what he could misreport, in a sense. What is the lowest possible value he could get the good for if he was going to misreport somehow? And let's charge him that. Very simple. He pays, sorry, not in this example, in this example, right? Where P1 is 0.2. This is the lowest price he could get it for if he was not truthful in the payment we discussed before. So let's design a payment mechanism where he actually gets 0.2, which is the lowest value he could have gotten for. Simple as that. So this payment is called the critical value payment. Okay? So the critical value says, what's the lowest value that the agent could have reported and still be allocated the good? Or his interesting sense, to make it a bit more general. Right? Now notice that it could change the allocation, right? So, if in this example, he reports less than 0.5, the allocation moves from slot 1, he still gets allocated, but he gets allocated in slot 2. But he doesn't care whether he gets allocated slot 1 and gets 2. His interesting set is satisfied. So the lowest he could bid in order to get satisfied, whether it's in slot 1 or slot 2, is having a value of 0.2. Okay, then you get the tie breaking, right? But we ignore that essentially. So you could charge him 0.2 plus some epsilon or something. But we ignore that epsilon. So the critical value in this example is 0.2 for agent 2. In the previous example we had, well, you can calculate it later yourself. Okay. So then the transfer is simply the minus of this critical value, right? Because transfers are things you give to the center, so payment is the opposite. Okay. If he is allocated, so you can always compute the critical value, right? Even for agents who are not allocated to good. So if he is allocated in the actual allocation, so greedy gives him his interesting set, then he has this transfer minus the critical value and zero otherwise. Okay? So then I'll give some example later. So the critical value is the minimum value the agent could have reported and still have received this interesting set. Note that the allocation does not have to be the same. It could be that, that at his value, at that minimal point, he gets allocated at a different point in time. But that doesn't matter. The other thing that you should realize is that the transfers, so how much he has to pay, are calculated on departure of the agent and not immediately. Okay? So what does that mean? So let's go back. Well, no, let's look at this example on the board. Okay? So if we would stop the auction right now in the first time slot, right? There's no second time slot coming. There's only one slot that goes to agent 1. That goes to agent 2, and he pays 0.5. Okay? Now the mechanism moves on to the second slot, and there appears to be another slot there. Maybe the mechanism doesn't know that in advance. With this agent that just arrived, right? The mechanism doesn't know that, have to know that in advance. The agent is here is already allocated the good, because we're talking, for example, about perishable resources. So he already has the good, okay? But he's still in the market. So he could have been available for the second time slot. If the market would stop here, his payment would be 0.5, but the market doesn't stop here, it goes to the next round. And the mechanism finds out that if he would have delayed his arrival, or if he could manipulate it, he could get 0.2. So at that point in time, his payment changes to 0.2. So at the moment, so he doesn't have to yet pay anything, so he only pays when he exits the market. And you can see that the longer the agent stays in the market, his payment can only go down. Right? So he can stay longer in the market and his payment can go down. So it's logical, the payment can never go up, because otherwise there's always an incentive for the agent to manipulate and depart earlier. Okay. So payment can stay the same, but it cannot go up. Okay? So the transfers are calculated on the departure of the agent. So when the agent departs the market, on his true departure. Okay? And so therefore, that's why we have assumed that the agent cannot depart later. He cannot report a later departure, but only an earlier departure. Because otherwise his payment could go down as well. Okay? Right, so there's a theorem here that said in a non-interesting set single value preference domain, any tools for online mechanism that is defined for deterministic decision policy and satisfies individual rationality, etc., etc. The mechanism must collect the payment equal to the critical value from each allocated agent. So this means, essentially, we can say we have an allocation function. We don't have to. Don't have to be optimal. So we have a specific allocation function, and we can then compute the transfers corresponding to that allocation function. And these transfers have to be equal to the critical value. So the interesting thing is here, that's quite nice actually, if we have an efficient allocation, that means that our social choice function is the same as the one in the VCG, then actually the transfers are, the critical values are the same as the VCG transfers. So I think, I guess I'm missing here the weak values as well. So, okay. So let's determine the critical values then in this sense. What are the critical values? So let's first look at first come, first served, and then read. So these are two social choice functions, and then we can just decide what. So for any social choice function we said before, we can apply the critical value payments or transfers. So let's do that. Okay. So what would be, if we do first come, first served, what would be the critical value payments?
0.5.
0.5?
Yeah.
Okay. Anyone else? Different value? So I'm talking about first come, first served, right? So what is the lowest the agent could report to still get the allocation? Okay, so first come, first served, remember that agent 2 gets allocated and agent 1 gets allocated, which is the same for green. So what's the lowest he could report and still get allocated? Yeah.
0.
0. Yeah.
First.
First come, yeah. The values don't matter. So the critical values are 0. Okay. So we have a social choice function, which is called first come, first served. We take this rule that we have to compute the critical value payments. We apply it, which depends on the social choice function. And here, the values don't matter in this social choice function, because even if you report, if this guy reports 0, it would still get allocated. And therefore, the critical value is 0. So the payment is 0. The same, obviously, for this agent. So what about greedy then, for this setting? What's the critical value there?
I think 0.5 for greedy.
Yes, 0.5 would be really very good. What about this agent? The second agent, what is, oh, I mean agent 1, what is his critical value?
0.6, 0.5 plus epsilon.
0.
It's again 0. Because this agent, so because if you look at the allocation, greedy allocation rule, so let's apply that. So suppose this one is 0, right? Then B2 gets the first slot, greedy. Okay. In the second slot, there's no competition. So B1 gets still allocated, even if his value is 0. Okay. Okay, so here's another example. So what's the critical value in this case? So here there's 3 agents. They all arrive, they all are in the market for both time slots. Okay, so what's the critical value here? So who gets what? And what's the critical value? 30 minutes.
Second highest bid.
Second highest bid. So which is
0 points.
So who pays? So B1 pays 0.7?
That's time step 1. And then the next step, B2 pays.
B2 pays 0.5. Next time step. No? Yeah? Is that true?
Maybe 0.
Absolutely not.
Okay, we're trying to find the critical value.
Yes.
So the minimum amount that they could pay and still get allocated.
Yeah.
So it's the minimum bet.
Hmm?
It's the minimum bet.
Minimum bet.
Minimum report.
Yeah. Which is?
0.7 plus epsilon.
Hmm?
0.7 plus epsilon.
So the first thing is to realize what is the allocation here? Who gets what?